Today we'll talk about the final lecture, about the final topic, which is the fluids. Okay. We have, I think, 4 things to talk about. The first thing is the density. Simply, if we have 2 masses, this is the first mass, and you can see that in the notes. This is the second mass. As you know, in physics, we study quantities. For any mass, we have M, which is M, the mass. And here also we have M2. This is a physical object. Now we are not dealing with a point mass, with an object, extended object, just like this eraser. And if we have this plastic piece, okay, 2 objects. The material inside this object, the atoms, the molecules, are distributed in different ways. Some of these objects contains number of these atoms or amount of material, like this. I'll draw the same thing here. You can see now there is no difference between them. We have 20 points inside each of them, one of them. But what if I put more atoms here? In this case, it will be more dense. We are in a class, 20 students or 40 students. The other class, the second class, is more dense. In this case, more dense, more material, more mass. So in this case, mass 2 is bigger than mass 1. Okay, anything to connect or to connect these 2 systems, we have for each object a volume. This is volume 1, that's volume 2, which is V, capital V. It is not the velocity. Okay, it's the volume now. Now the density is defined as the thing we need to find its density through this volume, which is the mass. The density is this sample. It is the mass over the volume. This is rho. I think it is like this, rho. Some people write it D or D, which is density, but in general it is rho, which is the mass divided over the volume. And from that we can know that the volume is equal to the mass divided over the density, or the mass is equal to the density multiplied by the volume. Now what is the units of it? The units of the mass is kilogram. The unit of the volume, it is meter cube. Some examples, it will be centimeter cube. It's okay. But it's a volume at that. Okay. Any question about this point? If we have, I will give you something else now, different. If we have 5 meters or 10 meters, and we have the time volume is 2 seconds. The time volume. Can you find the density of distance per the time? So the density of distance, which is x over the time, this is the velocity. So all the physics is connected together. This is a distance or a density of length per time. This is a distance of mass per volume. Any question about density? Now I think, different materials have different density. For example, you can see the table on the first page, which is from the book. The gold has now in this table the highest density, which is 19 point. No, this is per meter cube. It is 19 tons for the gold, for example. It is 300 tons per meter cube. The meter cube, almost, where's the stick? This is 1 meter. This is 1 meter, okay? And this is another meter. If we have a square, this is our square. It is a meter by a meter. Okay. And we have another dimension, which is the third dimension. This is a cube meter. If you can imagine this cube meter of gold, it is 19,300 tons. But of water, it is just 1,000 kilograms. This is not 19,000 kilograms per meter cube. Okay, this amount of water is 1,000 kilograms, which is just 1 ton. What about light things? For example, air. 1 meter of air is just 1 gram, I think. No, 1 kilogram. Air is 1.29 kilogram per meter cube. This is air. Now we have an example. We need to compute the weight or the mass of the air in this room. What else? I will tell you there's material heavier from gold. Mercury is heavy. Lead. Yes, lead is used in car battery. If you try to lift this car battery, it's very heavy, right? Because the density of lead inside it is very high. I will see now the most heaviest thing. I think it's the uranium or cesium, something like that. The most yes, the uranium. Its density, uranium, its density is 2,000 kilogram per meter cube. So just a small box of this material will be heavy to be covered by a car, okay? So it needs a heavy-duty truck to travel with it. Okay. Now let us compute some examples. The density depends on the mass distribution in the volume. So in this example, we have, for example, a ball of gold. This is the first one. A ball. This is a ball. We need to know what is the volume of this ball. The ball volume is, or depends on the radius. It is equal to 4/3 r cubed pi. Okay, I will give you these things if I ask you about them in the exam. R is 10 centimeters. R is equal to 0.1 meter, which is 10 centimeters. I just converted to meters. Okay, what is the volume? Now I have my calculator and I am very good in using it. I have 4 shift by 0.1 cube over 3, right? So the volume is equal to 0.004187 meter cube. Which is equal to 4,000 centimeter cube. No, wait. This isn't, yes, right. Right. I am asking about the mass. Find the mass. The mass is equal to the density multiplied by the volume. The density from the table, it is 19,300. It's kilogram per meter cube. So I need to use the meter cube quantity multiplied by 0.004187 meter cube. In this case, meter cube will cancel with meter cube. We know how to do this. This will be equal, the unit is kilogram. I need just to multiply the density is 19,300. Okay. It is 80. Wow. 0.84 kilograms. So the ball, just like this, which is 80 kilograms. So why not? Just this ball is 80 kilograms. It's very heavy. It's almost, I am 90. Okay. Now, the next question. A cube of cherry wood with L. This is the cube. With L is 30 centimeters. This is 30 centimeters, okay. This is what? 30 centimeters. Its volume is X by Y by Z. So the volume will be equal to 30 centimeters, means 0.3 meter. Okay, so the volume will be equal to 0.3, which is X, multiplied by the same thing, which is y, multiplied by 0.3, which is z. If we have this shape, which is not a cube, and we have this is x, this is y, this is z, then multiply them by together, you will have the volume. This will give us 0.027 meter cube. This is the volume. What about the density? The density from the table. So the mass is equal to the density from the table. It is 800 multiplied by that volume 27 will be in kilograms, because we have kilogram per meter cube, we have meter cube there to cancel, and this will give us 800 multiplied by 0.27. It will be 21.6 kilograms. It's a box, just like this. It's larger than this box, than this ball. This is 10 centimeters. This is 10 centimeters. Also, this is 10 centimeters. This is our box. This box of wood is just 21 kilograms, but this ball of gold is 80 kilograms. There's too much material inside this mass. You can compute, for example, a neutron star material. It is just a neutron. Because of that, they told you 1 spoon of this material, neutron star, weighs 1,000 tons. Okay. The third one, the weight of, where is this? Here. The third one is, this room is Gardner Hall 230. We need its mass, the air's mass inside it. This room is, it is not a cube. Okay. Its dimensions x equal to 12.2 meters. This length is 7.6 meters. Small. But we need to assume just these dimensions, okay, as the example. 4 meters. So the volume, as I told you, is x, y, z, which is equal to this multiplied by that, which is 12.2 multiplied by 7.76 multiplied by 4. This will be equal to 12.2. 7.6 4 is, so the volume is equal to 370.88. We can consider it as 371 meters. Okay. What is the mass? It is equal to the row of air at 20. If we increase that, if we change the temperature of the material, it will expand or crunch, but this will change its density. This will affect gases more than solids and liquids. Okay. Now, the density is 1.29 multiplied by this volume approximately, which is 371 by the volume, which is I approximated to 1.29 multiplied by 371. It is equal to 400.6 kilograms. So the air now in this room is 478 kilograms. It's not light. Okay. The blood now. The last example, the blood inside our body. How much the weight of that, or the mass? I'm talking about the mass. Okay. The weight is the gravitational force for that mass. I'm talking about the mass. Okay, for the blood. Okay, the volume is given as 5.2 liters. Wait, no, not this one. I didn't compute the mass of the bottle of water. Okay. 1 liter is equal to 1,000 centimeter cube. Also, it is equal to 0.1. It is 1 over 1,000 from a meter cube. This is 1 liter. So I need to convert it to a meter cube. So it will be, the volume will be equal to 5.2 liter multiplied by each 1 liter is equal to 0.001 meter cube. I am using now the first material to solve that last lecture example. I will remove it letter with letter. It will be 0.0052 meter cube. This is the volume of our blood. Okay, what is the density? Rho. From the table, it's dense, not kilogram per meter cube. So the mass of the blood is equal to, we can find it, it is multiplied by 1220, it is 6 kilograms. 6.344 kilograms. For a bottle of water. Okay, this one. The volume is equal to 0.3. I think I put it, or half a liter. No, 0.3 liter, which is 0.0003 meter cube. Okay. The density of water is equal to 1,000 kilogram per meter cube. So the mass of it is equal to 300 grams or 0.3 kilograms. Any question about density? Now I move to the next quantity. Which is the pressure. The pressure, if we have an area, this area we can name it by A. And we have a force. This force should be perpendicular or normal to that area. For example, this force, we cannot compute the pressure directly from it. We need to use the perpendicular. So we need to use sine theta with it. But we will not talk about it. Okay? We need just the perpendicular force. The pressure in this case is equal to the force over the area. The area, it's x by y, which is in meters squared. So its unit is Newton over meter squared, which is named after this person, Pascal. You may see it PA or Pascal like this. Okay. Now we'll see, we will understand what is the pressure by doing this example. The pressure is just like this. When you press on the sponge on your chair, you can feel that pressure. Okay, the first example, a bottle of water. Again, this bottle of water has a base. This is the base. I give you the area of that base, which is 7 centimeters squared. It's area. And the mass of this water is equal to 0.5 kilograms. It is the ordinary water with us. This is the mass. We need the force. What is the force? It is the force downward. It is the weight, which is equal M multiplied by G. It is simple to find the force. This is the force. So the force equal to the weight, which is equal to M 0.5, G is 9.8. It is equal to 4. I think. Newtons. Now, what is the pressure? It is equal to the force over 8. 8.5 over 7. So it is equal to 1 point something. It is equal to 1.2142 Pascal, PA. When you put the bottle of water on the top of your hand, this is the pressure, just 1 Pascal, 1.2 Pascal, like that. Okay? Now let us see different objects or examples. We will talk about atmospheric pressure. It is very high. And we will see that. Now the second example, a force applied by your hand if the force is equal to 2.5 newtons. It is equivalent to 0.25 a quarter kilogram. It is less than the mass of the bottle. The bottle has a mass, this water, half kilogram. This is half of it. So you push by a half of this mass. Now, on a needle tip, you see that there's a balloon and there's a needle tip. Initially, we have a needle which has very small a, which is equal to 2.5 multiplied by 10 to minus 7 meters squared. We need to compute the pressure in this case. Pressure is equal to 2.5 over this 2.5 multiplied by 10 to minus 7 will be equal. This will cancel with this. This will be to the up. It will be 1 multiplied by 10 to the 7 Pascal. It is 10 millions. when you use a needle and just push by 2.5 newtons, it is 10 million Pascal. Because of that, they use it to inject anything inside our blood. Okay. What about our finger? Okay. Now, this area, it is not small. It is there's a typo here. The area of this finger is not 1.5 meter squared. It's like this. No, it is 1.5. I think it is multiplied by 10 to minus 4. Yes. Just 1 centimeter. Meter square. This should be centimeter square, but I convert it to meter square without multiplying by 10 to minus 4. Just put it in part B, the second example. Now, the force is given. What is the pressure? Is equal to 2.5 over this 1.5 multiplied by 10 to minus 4 equal to 1.667 multiplied by nothing. No, multiplied by 10 to the 4 Pascal. Okay, this pressure is equal to almost this number, 1.666.7. No, we need another point. This is 16,000 Pascal. Now, for the atmospheric pressure, we name it PAT, atmospheric, is equal to 100,000 Pascal. It is 10 times more than our finger pushing here. But we cannot feel it because we have it from the top of our hand, from the down of our hand, and our blood from inside pushing outside to reach the balance or equilibrium at our skin. Okay. The third one, yes, we have the camel and the horse. The camel legs or foot, when he put his foot here on the sand, its area will be bigger, and already its foot area is big. Because of that, its pressure on the sand is low. Because of that, mostly it cannot go inside the sand, the camel. So let us see this. For the camel, his mass is equal to 1,000 almost kilograms. So its weight is equal to mg, which is 1,000 multiplied by 9.8, which is 9,800 newtons. His weight, okay? This weight is focused on 4 foot area. So the area is equal to 4 multiplied by the area of just one of them, which is 350 centimeters. I will convert it to meter. It will be 0.35 meter square. This is the area. So what is the pressure for camel? It will be the force, which is 9,800 over this quantity, which is 4 multiplied by 0.035, which is equal to 70,000 Pascal over the sand, because it has 4 legs with this area. Let us talk about the horse. Same thing. We have for the horse, the mass of it is I think 800. I put it 700 kilograms. Then the weight is equal to which is mg, and the area is equal to 4 multiplied by 0.008 meter squared. I convert from centimeter squared to meter squared. So the weight, which is the force, is 700. It is 6,860 meters. This case, the pressure for the horse is equal to the force, which is this amount over this area, which is 0.008. It is 214,375 Pascal. It is too much more than the camel's pressure. The camel is heavier than the horse, but its pressure is 70,000. Here 200, 3 times, because his foot area is smaller than the camel's, and because of that, horses inside the sand, you can see their legs will go inside the sand, will dive inside it. Okay. Any question about pressure? In this case, I solved many questions about it. Now I will talk about atmospheric pressure. I will go from here to let you see everything. Okay, let us share the monitor. Here you can see the camels who cannot go inside the sand, not like the horse. Okay, the pressure, air pressure or atmospheric pressure, the density, at first, the highest, or the highest of the atmospheric layer around the earth is not determined by a number. Okay, it will go to infinity, but the density of air particles at the top here will go to 0. So here in the top we have low density. Because of that, we have low pressure here. Here at the surface of the earth or the ground, we have more density, and all of this column is above us. Because of that, we have higher pressure, because we have more mass. What about, okay, but we are not talking about the mass, we are talking about the force. The pressure is equal to the force over the area. Over the area. The force in this case, it is the weight of the air column above our head. You cannot see what I'm talking about. Okay. So I'll stop sharing. Here, the pressure is equal to the force, which is the weight over the area. The area, assume it was just 1 meter square. So the column of the atmospheric air above our heads has a mass, and its mass is not small. As you see here in the room, we have more than 200 or 300 kilograms for this air. Because of that, we have this air above our heads has a mass and has weight, which is a force. Over any area here, it will be a pressure. This is atmospheric pressure. And as I told you, P atmospheric is equal to 100,000 Pascal. It is not small. Didn't try too much. Okay. Now we have this example, as you see. Find the mass, the air mass above your head, above your hand. Yes, this is our hand. If you look here, we have each 1 Pascal is 1 Newton per square meter. The atmospheric pressure is 101 almost kilopascal, which is 100 kilopascal. There is another unit which is not important to us, which is pound per square inch. Now, for each pound, for each square inch on our hand, we have 14.7 pounds of air above it. Okay. And we have another measurement, which is the bar. It's another measurement for the pressure. Each 1 bar is equal to 1 atmospheric pressure, which is 10 to 5 pascals or 100,000 Pascal. As you see, we have a pressure from the top, from the down, and I'll stop sharing here. And we have our blood pressure from inside. This all together will balance all the pressure on us. For example, outside the Earth atmosphere, with a vacuum pressure, the blood will, our body will bleed if we are there without any cover, because the blood inside will be higher than the blood outside. Also inside the sea, down, the pressure will be very high and it will crush anything. Now, if we need to compute, as you see in the example, if I ask you how many kilograms or how much the force above your hand, and this is our hand. This is the area of my hand. I assume it A is equal to 8 multiplied by yes, 8 centimeters, its dimensions. I assume it as a rectangle. 8 centimeters by 15 centimeters. So its area will be 8 centimeters, it is 0.8 multiplied by 0.15 meter cubed, meter squared, I'm sorry. This is the area. I assume it as a rectangle. And the pressure is 100,000, which is 10 to 5. What is the mass? What is the force? Okay, or the weight above your hand? The force is equal to pressure multiplied by the area. The pressure is 10 or 100,000, or looks like this, multiplied by this, which is here 120 multiplied by 10 to minus 4. This will be equal to 120 kilograms. Okay, now there is 120 kilograms here. I cannot lift them. 100 kilograms. I am 90. It's heavier than me. Okay, and we have the same thing. The air effect will come from the down from our hand. In this case, my hand will be crushed like this. It will be like just a paper. But because the blood pressure from inside keep it like this. Okay, so we have heavy. This is 100. It's this force. This is the mass. Okay. This is here. Yes. This is 1,000. And 200 newtons, which is equivalent to, if we divide over G, which is almost 10, it will be 120 kilograms. This is the mass here. Okay. Any question about pressure? This is air pressure. Air's density is 1.24. Water density is 1,000 times more than the air, right? Because of that, the pressure inside the water will be 1,000 times more than the atmospheric pressure. Because of that, the submarines should be very heavy-duty materials. Now I will talk about Archimedes principle, which is the last thing. I will share my monitor. You can see any videos any video you like. Now, Archimedes principle. You may read it as Archimedes principle. It is simply, if we have any object inside any fluid, fluid means air, gas, or liquid, just like water or oil or any liquid material. This will face, or there is a force of buoyancy from downward to upward. Okay, for example, if this mass is 7 pounds, if we put it inside water, for example, it will be 4 pounds. That means we lose, or it lost 3 pounds. That's because we have a pressure or a force from downward to upward on this mass. This force is 3 pounds. As to understand that, this mass will remove, because it's volume, 3 pounds of water. Okay? We are talking here on pounds, but we can do the same thing with the newtons. Okay. The Archimedes principle has many applications. For example, we can use it in boats. We have the gravity, which is the weight downward, and the buoyancy, which is upward. Because of this volume, this mass removed just as a mass of water equal to this mass, and this mass of water will affect by this buoyancy force upward. Okay, that's happened because the difference of pressure between the top of this mass and the bottom of this mass. There is a calculations, and we don't need to talk about it. Also, the hot balloons are doing the same thing, because the hot air is less density, has a less density than the cold air. Because of that, this material is lighter than this air, is lighter than the other cold air. Because of that, there is a buoyancy force upward. If we control the all over buoyancy, all over the density of the object, as you see here in submarine, if we remove all the water from the reservoir here, it will be just fill of air, okay? Because of that, there is a buoyancy force upward more than this case, which is there's a water inside it and its density is more. So they can control the depth of this submarine inside water by putting water or removing water, or by increasing density or lowering density. That's just talking about Archimedes' principle and its applications. There is a calculation that we don't need to talk about. Okay. Any question? As I said, there's another homework for the last material. Stop sharing. Stop recording.